So good morning. So I would like to start by thanking the organizers for giving me the opportunity to give this talk here. So the title of the talk is Hamiltonian Quantum Computing with Superconducting Qubits, and it is basically based mostly on this paper that we recently published. And it is a work that I've done partially where I was before in Aachen and where I'm now at TU Delft. So the talk is a theory talk. I don't know how many of you are familiar with what I mean actually by Hamiltonian quantum computing, which I actually realized that sometimes in the literature is also used to include the adiabatic quantum computation. But at any rate, it's not directly adiabatic quantum computation, but there is a, let's say, deep relation between Hamiltonian quantum computing and what we call adiabatic quantum computation. Okay, so let's get started. So this is just an outline of the talk. So I will give a brief introduction. Then I will introduce the model that I will treat. I will then discuss some basic numerical analysis for systems with small size. And then we will map everything to qubits, and then I will explain let's say, the superconducting qubit version of the problem. So, because, as you will see at the beginning, I will not directly talk about qubits like transmons, because the model is more easily discussed in terms of a particle that hops on a line with an internal degree of freedom. You can think about an electron, maybe, although the fermionic nature does not play any role. But then we will map the problem to qubits. Okay, so let's start with Hamiltonian quantum computing. And the idea is actually a very old one, and it goes back to one of the early papers of quantum information by Feynman. So this is 1986. And actually, more or less the same model is discussed also in this work by Parrish in the same year. And so Feynman, at the beginning, when he was thinking about quantum computation, wasn't thinking about, let's say, neither the adiabatic model of quantum computation, nor the, let's say, circuit model of quantum computation, where so in the standard model of quantum computation, the idea is that we implement the gates using essentially time-dependent Hamiltonians. So there is a routine that implements a certain gate. But he was thinking actually to conceive a computation with a time-independent Hamiltonian that was somehow automatically, autonomously doing the computation. And so the paradigm can be stated in this way: performing a quantum computation with a time-independent Hamiltonian, and in which the system evolves in a linear superposition of all the intermediate computational stages of the computation. So here I will try to explain what I mean by this. So the Hamiltonian that Feynman constructed was essentially this one, and it acts on a system of data qubits that encode the quantum information. And in addition, there is also a so-called clock system, which was essentially necessary to keep track of the stages of the computation. And what the Hamiltonian, what I call here the Feynman Hamiltonian, does is that, so it's a sum, so if we want to apply m unitaries on the data system, the Hamiltonian is a sum of m terms, and what these terms do is basically applying a unitary to a certain unitary to h data, so to the Hilbert space of the data qubits, and it also shifts the state of the clock. Of course, since it is a Hermitian operator, there is also the inverse process. It can be easily shown that if we define these states here, where this phi 0, phi naught is the initial state of the data qubits, So it's easy to understand that this has the interpretation of an intermediate state of the computation. It is easy to show that the system always evolves into a linear superposition of all these states. So in principle, there is a non-zero probability to find in the system in the final state. Okay, so it is also easy to show that the dynamics maps unitarily to quantum work on a line with m+1 sites, and so it is actually independent of the gates of the unitaries that you're applying. Okay, so you can see that, however, the main problem with this kind of Hamiltonian is the presence of a clock system that is m+1 dimensional. So also here we have, with this m+1 dimensional system, at least a weight-free term in the Hamiltonian, because we know that we need to do at least 2 qubit gates. Okay, but then what's the connection with adiabatic quantum computation? Is that actually Kitaev, in his book, constructed, based on the Feynman Hamiltonian, another Hamiltonian that actually has now as a unique ground state the so-called history state. And the history state is an equal superposition of all the intermediate stages, all the intermediate states of the computations that we defined before. He constructed this Hamiltonian starting from the Feynman Hamiltonian and summing some terms. And as you see, the probability of being at the end of the computation is 1 divided m+1. So it has, so it's not like 1 divided 2 to the m, which would be bad. And Kitaev actually used it to construct an important proof in quantum computational complexity theory, that is the QMA completeness of the local of the k-local Hamiltonian problem. And in addition, this construction is basically the basis for proving the equivalence between the circuit model and adiabatic quantum computation, as was done by Aronov et al. In 2004. But if we think about a practical implementation, the main problem, as I said, is the clock. And now I will try to explain why. So we can implement the clock system in different ways. So here we have what I call the cheating clock, because we just take an m+1 dimensional quantum system, but it's clearly unphysical that we can have control on a single system that is not made of small parts. So an alternative might be to use a pulse clock. So I think it's quite intuitive what I mean. We have the clock is made out of qubits, and so where there is a 1 essentially that denotes the state of the clock. So in this case, if we use this clock construction, the Feynman Hamiltonian has is 4 local. That means that it has a weight 4 interactions. And also you can construct a domain wall clock, but an alternative, so these are all constructions with a so-called global clock, where we have only 1 clock. But an alternative might be to use local clocks, which means that essentially each qubit has its own clock. And a way to do this is not necessarily to have a specific clock system, but to somehow, let's say, encode the role of the clock in another variable of the system. And this is essentially the idea that I'm describing here. So let us suppose that we have a particle. The particle has a 2-dimensional degree of freedom, the internal one, where we encode the quantum information. And the point is, the particle can hop on these sites. And when hopping takes place, like in the Feynman construction, more or less, there is a unitary so in this case, single qubit unitary that is applied to the internal degree of freedom. And so you understand that if you know, like for instance, the particle started here in a certain state, then if you know the position of the particle, you understand that it's the position of the particle that plays the role of the clock in this system. Okay, so this is basically the idea that we will build in now. Okay, so now, of course, if we want to do single qubit gates, that is not enough, of course. Like in this case, we would have many particles that hop on their respective line. So for now, we can only do single qubit gates. And the idea is, if we work with local clocks, in order to do 2-qubit gates, we need to coordinate the clocks in order to guarantee that the order of the computation is performed in the correct way. Okay, so this leads us to this model that I will now describe, and that was essentially introduced by Lloyd and Terral in 2016, but somehow it is the evolution of many works in the literature, so I here just cite some of them. And the idea is now that we consider still hopping particles, but now they are organized in a rotated square lattice. So again, the particles can hop on the horizontal line. So here, 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 here. And when hopping takes place, we have a unitary. And so as you see, there is always one particle per line. And actually, the Hamiltonian is constructed in such a way that the hopping between different lines is not possible. So that's why the nature of the particle per se does not play a role in this case. At any rate, what's the idea? So this is what I call the initial string. So string, I just mean I can just connect the particles in this way. So this is the initial configuration. We can start the system, the internal system in, I don't know, internal state all 0 as usual. And so what do we want now is we would like to guarantee, so we would like to implement a one-dimensional quantum circuit, that's to say only with nearest neighbor gates. And we would like, I claim that we would like the strings, so the particles, always to form a so-called connected string configuration, like this one, but not a disconnected string configuration where you see that here the string is essentially broken at this site. And the reason why we want this is that if we guarantee that we always work in this subspace, it is guaranteed that a one-dimensional quantum circuit is implemented in the correct order. So maybe it's not immediate to see it now, but it is the case. And so how can we do this? So we construct this Hamiltonian. The Hamiltonian is given by two contributions, a Hamiltonian that I call H-valid, and a hopping Hamiltonian. So the hopping Hamiltonian acts on the plaquettes, essentially, and it applies the gates that we want to do to the internal degree of freedom. But the important role is played by the Hamiltonian H-valid, because it guarantees that the connected string subspace is the ground space of the Hamiltonian H-valid. And in order to do this, so here we have, so this is the form of H-valid, we basically put attractive interactions, so with a minus coefficient here, so with a negative coefficient, on all the edges of this lattice. Here the n denotes essentially a number of operators at a site. And in this way you actually realize that the connected string configurations all have the same energies. And actually if you have a broken string like here, you would have a penalty that is given by plus delta. So then if we guarantee that the hopping is small compared to the gap, essentially, we can just project the Hamiltonian onto the connected string subspace and obtain an effective Hamiltonian. So as you see, the whole point of this construction is that here you only have weight 2 interactions, and they are also relatively geometrically local. Okay, so this is just to give you an idea of how the string propagation works. Again, the string propagation is independent of the gates that you're doing. So we start the system here. It evolves for a certain amount of time, and you see that it evolves somehow in a bunched way. So here I'm plotting the. So these are the probabilities of finding the particles at the site, and then you arrive somehow at the end of the computation. So so essentially you need to know. So the dynamics is in principle is solvable analytically after you do the projection. So you need to know more or less when the string is arriving in order to understand when to measure, so to extract the quantum information. So I will give you some more details later. Okay, so, but as I said, for now we are doing only single qubit gates, but single qubit gates are not enough. And so we would like to construct 2-qubit unitaries at least. And so here I will describe briefly how to do a C0 in this model. And in order to do a C0, we need to modify a region of the lattice, so where we want to perform the C0. And in particular, the C0 will be implemented in 2 steps. And the way this works is somehow reminiscent of a railroad switch, where the control particle, controls the direction of the target particle. So here, let us consider this part of the lattice. And so we have a control target, so nearest neighbor C0, and a spectator particle. So let us suppose that the spectator starts in whatever state. The target is in 0 and the control is in 1. And of course, we would like at the end to have control in 1 and target in 1. And the idea is that if the control is in 1, we just send the particle here and we apply an X gate. So then there are hoppings that keep the string connected in this way. And then finally, the particle hops at the end of the computation of the region. Of course, this has to be intended in a unitary dynamic. So then you would also have the opposite process. And so essentially, as I will argue later, if I have time, the way this C0 works implies somehow that you know that the string is moving forward. So it is moving, in this case, from left to right, which is actually ensured by somehow the shape of the lattice that we are considering. Okay. So how can we do this? Okay, maybe this equation, you will not be able to understand it immediately. But the point is that if we have essentially the opposite configuration in which instead of the particle being here, the particle is here, we just give an energy penalty to that configuration. So exactly in the same way as we did before with broken string configurations. And that essentially would guarantee again that the incorrect configurations are not in the ground space. Okay, so this is just some simulations of a single C0. So we just consider a single C0. I also remove the spectator qubit because doesn't play much of a role here in the simulation. So we have an initial configuration. The particle is here. The particles are both here, and control is in 1 and target is 0. And for us, we would have success when the particles are both at the end and in state 1 and 1, internal state 1 and 1. Okay, so this is just more or less how the system evolves in time. So here the blue one is the probability of success, and the red one is the probability of error. They don't sum up to 1 because simply you can have configurations in which neither of these cases happen. And as you see, the probability of success reaches a maximum here at JT equal 3. But I would like to point out that you start to see that the probability of error, although small, starts to increase in time. And there is actually a reason for this, and it is connected to the fact that in order to implement for this scheme to work, again, we need to guarantee that the moving forward of the dynamics. Because if we then take the average over a long time of the probability of error and the probability of success, eventually they will average out and they will be the same. And the reason for this is that eventually the Hamiltonian is somehow completely degenerate in the spin degree of freedom. So essentially, the wrong configuration in which you have 1 and 0 has the same energy of the correct configuration. And this means that if you start in a correct configuration, then you have barriers to go to an incorrect configuration, but eventually the system will tunnel there. And so it will be a process that will essentially repeat, and eventually we will have an averaging of everything, and the probabilities will be the same. Okay, so in the same way we can construct the Toffoli. I will just go quickly here, although the construction of the Toffoli is kind of important. Okay, we have two controls, and the target is sandwiched between the controls. And the point is, we want now to do exactly the same trick, but with two particles. So depending on the state of control 1, we go either here or here. In this case, we go here. And then there is hopping. And now depending on the state of this control here, we either go here or here. So in this case, we go here. And at the end, we arrive at the end of the lattice. Okay, with the same idea, it's easy to understand that we can do any controlled and controlled unitaries. So now we'll briefly mention some studies, some numerical studies of the string propagation. So this is in the case, so without projecting, so just by taking the full simulation. So only up to lattice n by n, so 5 by 5 sites. And here what I'm plotting is actually so this operator is essentially, so the average of this operator is essentially the average position of the center particle, which is representative of the string motion. And as you see, so in agreement with so this is in agreement with the analytical solution that you get with the projection. At the beginning of the computation, you see that this position, so this particle, moves essentially at a constant velocity, that is approximately 0.6 sites per dimensionless time. Okay, so this is a simulation which over delta divided 1 divided by 50, and so you know that given the structure of the lattice, you expect the computation to evolve, so to propagate linearly in time, which is important from because I mean it will scale linearly with the number of gates. Okay, so then we also did some small studies of the effect of disorder, which in this kind of systems is actually quite important. And what I mean by disorder in this case, so we've studied disorder on the hopping parameter. So that's to say we are just making many simulations where we put randomly a hopping on each plaquette, so Gaussianly distributed. So as we see, in this case, we have 10% disorder. The string propagation is more or less the same as the ideal case. So let's say that this disorder on the hopping parameter is not be too problematic. But a more serious source of disorder in the system that eventually will lead to a localization is actually the disorder on the on-site energy. That's to say, we randomly put terms on each site that are proportional to the number operator. And if we have disorder on the on-site energy, we see that, so in this case, these are different curves with increasing amount of disorder. So the disorder goes from here to here. So sigma here is the standard deviation of the disorder, and divided by j, the hopping parameter. So you see that if sigma divided by j is 0.1, basically you don't see any effect of localization. While essentially when you have, in this case, sigma where j is basically 10, the string would be fully localized. So you would like at least to work in this regime. And eventually, in the qubit implementation, potential qubit implementation, this kind of disorder will be essentially a disorder in the Josephson junction energy, so the Josephson energy, and eventually we will end up more or less here. So we will not be in this curve here. Okay, so now after talking about particles hopping on a line and interacting, now it's time to map the whole system to qubits. And this can be done by dual rail encoding. So the idea is that we substitute each each side of this lattice with two, in this case we will consider 2 qubits, 2 transmons for us. And the idea is that the vacuum will play, so 0, 0 will play the role of the vacuum. 0, 1 will play, so will mean that the particle is there in the internal state 0. 1, 0, the particle is there in the internal state 1. The 1, 1 is, so we just throw it away and it is not used for our purposes. So the first thing is, so the dual rail encoding is good because it allows us to map the system to qubits, and so maybe so we can use the flexibility of superconducting qubits to design the interactions. While maybe if we were thinking about a particle that was hopping on a line and then applying these gates was let's say kind of hopeless to think about a system like that. But however, it is bad for from another point of view. That's to say that now it's really the excitation that is our particle. And as you know, let's say the excitation in a superconducting qubit is not as a stable object like an electron maybe. Let's say that it has a much shorter lifetime. Okay, but at any rate, so this will be a way, so we will have, of course, problem of T1 like somehow in any implementation. Okay, so then we need to translate the interactions in terms of qubits. And what I claim is that the attractive edge interactions, so on the edges, essentially for transmon qubits will be cross-care interactions. And the hopping interactions will be hopping interactions that are usually called flip-flop interactions. Okay, so let's first start with the so-called easy interactions, flip-flop interactions in this case. Okay, so this is, okay, so sorry. So this is actually the layout of the whole system. I just point out that maybe it wasn't clear before, so I didn't say it before, that, so as you see, the different colors of the transmons denote different frequencies. The frequencies in this model, so in this case, will be the equivalent of the on-site energy. And so that's why I was saying that before that the variability in the Josephson energy will basically modify the on-site energy, and that is what will cause disorder. But as you see, there is some freedom in the model. So this, I didn't show it before. But the point is, maybe it's also a bit intuitive to understand it, is that since we have always one particle per line, so we always put one excitation for each line, then it is necessary to have the same on-site energy here, so the same frequency, but you can actually detune the lattice. That's to say, in this case, I consider a scheme with 3 frequencies, so green, red, and blue. And although this wouldn't play a role in the ideal model, it does play a role when we consider that we have spurious term and we want to mitigate let's say the crosstalk or the spurious interactions that we have. Okay, so these are just some, let's say, parameters. Okay, so now an important point is that so the hopping interactions are responsible also for the application of the gates. And so we are usually, when we think about universality, we usually think about doing universality with C0, Hadamard gate, and pi over 8 gate. But my claim is that given the Hamiltonians that we have available now in circuit QED with Transmen qubits, due to the time reversal symmetry of these Hamiltonians, we can only have Hamiltonians that are real, so or can be made, or they can always be made real. And so in our model, this implies that we can only achieve universality with real gates. This is possible, and this has been shown in 2002 by Xi, and then also in another paper by Aronov, although it is a universality that uses ancilla qubits. And so this is actually also why it is also important to have a direct way of doing the Toffoli. An alternative way of constructing a universal set of gates is to use, in this case, we will have only 2-qubit gates and a single qubit gate. That's to say using C0, Hadamard, and control Hadamard. And the reason is that it's quite easy to show that using these gates here, we can easily construct a Toffoli. Okay, so now how do the gates translate in the system? As I said, they are the hopping, and hopping in a system of Transmen qubits can be, so flip-flop interaction, can be achieved using, in this case, simple capacitive coupling. So this simple scheme with capacitances here, so the crossing of the capacitances is, let's say, kind of arbitrary. But however, you see that this scheme somehow reproduces gives the idea of the matrix element of the X gate. However, capacitive coupling gives gives a coupling of a certain sign. And for this reason, in order to achieve universality, we need the Hadamard, and so we need to engineer a way to get a sign change. And a possible way of doing this is to use the dispersive interaction with a resonator. So that's to say, in order to implement the Hadamard, we use 3 capacitances, and then by the dispersive, let's say, generalized Jaynes-Cummings interaction, it is easy to show that you can get a sign change of the interaction. So, and this will allow to do actually the Hadamard gate. Okay, so then, so these are somehow the easy interactions. Then we also need to engineer some cross-Kerr interactions, and the point is that we would like these cross-Kerr interactions to be strong, and in addition, we don't want the coupler to induce spurious interactions in other parts of the lattice. In particular, so you see that the cross-Kerr interactions, so these attractive interactions, are between transmodes that are detuned from each other. So in general, a coupler would have the tendency, let's say in Transmen qubits, you will always have the tendency to have hopping interactions with every coupler you come up with. But the problem is not too much the hopping from here to here, so from here to here, because however, we can still rely on the detuning of the transmodes, but it is actually more, let's say, the unwanted interaction that this Transmen here mediates between this qubit and this qubit here, because then it would sum to the wanted one, and then we will kind of start to lose control on this interaction. Okay, so ideally, however, we would like to completely cancel the hopping from here to here, and that would also guarantee that we have somehow a small interaction between qubits on the same line. Okay, so in order to do this, we came up with this coupler that is formed by essentially an inductance, a Josephson junction, and array of few junctions, 4 in particular. And so here I will just describe essentially what's the basic idea. Let's say that this is somehow an evolution, again, of something that was already present in the literature. And the idea is that of filtering. However, the point is that here we have a particular potential that if we set the external flux to a certain value, we can expand the potential around the minimum. I mean, here we should, so this is the coupling potential that is given by the coupler. After the expansion, so phi, this variable phi is the phase difference from here to here, we end up with this coupling potential. And as you see, in the end, what we do is to rely on the different periodicity of the array of junctions and the Josephson junction, and so that ideally we can have essentially a 0 quadratic term that will actually give the hopping interaction, but still have a non-zero quartic term, which would be actually more or less the same as a Josephson junction. And this ideal condition will be if we, so alpha is essentially the ratio between the Josephson, the small Josephson junction and the Josephson junction of the arrays. And so this condition is achieved if we manage to match this condition. So if we manage to set these parameters to 0. Although I here put an approximately 0 because ideally, I mean, you also have a hopping that is given by the capacitance. So you would like so this shouldn't be really 0, but approximately 0. Okay, so that essentially at this working point, the coupling potential is essentially, let's say, approximately fully anharmonic. Okay, so this is just to sum up. So with this kind of coupler, we can get relatively large cross-care interactions, and ideally 0 unwanted hopping between transmons on different lines, and also the induced next nearest neighbor hopping will be of the order of 100 kilohertz. That is more than 1 order of magnitude smaller than the hopping that we would like to engineer. Okay, so so this is just again a global layout of this construction. So how this works? So these are basically feed lines where we put the excitations. Then essentially the internal structure of the circuit does the quantum computation, and then we need to extract the result of the quantum computation by measuring the qubits at the end or also in the middle of the computation. So as you see, in this kind of construction, the nice thing is that you don't need any control so you don't need essentially internal control lines, and you don't need to do gates with a time-dependent Hamiltonian. Okay, so here I don't think I have much time. Just to tell you that we also constructed an alternative model. And basically, the alternative model has, let's say, a different connections, but eventually the dynamics of the system in this case maps to that of a quantum walk on a line. And so in this case, it maps unitarily to the Feynman problem. And in this case, the gates will be executed in a snake-like fashion. And since it is like a quantum walk on a line, we can also engineer some perfect quantum state transfer techniques to guarantee that the end of the computation is reached at the end. It's reached with probability 1 at a certain time. Okay, so these are essentially the conclusions. So I've described this model of Hamiltonian quantum computing with a Transmen implementation where we can achieve universality with real gates, and also we devised a cross-Kerr coupler that can give, let's say, purely nonlinear interaction. And with this, thank you for your attention.
Okay, thank you very much. Now we have time for questions.
So you've got the numerical work looking at how the strings propagate,
yes,
and the success probability at the end.
Yeah.
And it looks good for 2, 3, 4, about 5, and the probability is now lower per
Shall I go to
qubit. Yeah, so have you looked at how that is scaling for large numbers of qubits? You had that, so it's a nice linear growth, but then how?
So
what the maximum probability is?
Here,
yeah, here you see
okay,
it's
you see
not
that,
meeting those lines.
It doesn't reach the end.
Yeah. So how is that gap scaling?
Yeah, that's a good question. No, I haven't looked on that, but I have. So eventually, what happens? So I don't know exactly what the scaling is, but what happens is that by just reasoning entropically, the string will get stuck in the middle because there are so many possibilities. But I don't know how that scales. But still, the point is that so you would like actually to measure. So that is an interesting point because it is not trivial to understand how to optimize the search for the string, because you might say, okay, I measure all the times, but that's wrong because then you have quantum zero and you never, yeah, exactly. Yeah, but then you have knowledge of how, so the ideal model is numerical, so is analytically solvable. The ideal, by making the projection. After you make the projection, is solvable analytically. Yeah.
More questions?
Why do you encode everything into 2 Transmen qubits instead of using a single Transmen as a qubit?
Because, okay, it's because you need essentially a Q-trit. Because you see that you need 3 levels. Ah, okay, no, yeah, but you cannot use the third one because it doesn't have the same energy. So you need the energy of this state and of this state, they have to be the same. Yeah. So maybe you can think of doing it maybe with a fluxonium in that way approximately, but then it gets really hard to understand how to do the hopping. So in a certain sense, this dual rail encoding makes things somehow easy from the hopping point of view, although then you have some disadvantages, of course. Yeah. Yeah.
Yes.
Hi. Have you done any estimation of the resources that would be required to run an algorithm in this kind of architecture?
The resources?
Yeah, how big of a circuit would you need
in order to implement? Okay, how big of a circuit one could do now, I have an estimate of that. So in principle, so if we consider typical T1 times of superconducting qubits, so the point is that the scaling of this problem is not that bad because, so if we, so the point is we put the excitations and then after, I don't know, 50 microseconds somehow we will lose them. But the point is that, so this particle, so let's say even if you have hopping here, the relaxation of this excitation is exactly the same as a normal superconducting qubit. So as a single qubit. And if we consider like 50 microseconds, I estimated that you can construct up to a 15 by 15 lattice in principle, which will make it till somehow the end of the computation.
So that was not exactly my question.
Okay, sorry.
I was looking for how big of a circuit would be needed in order to implement an algorithm of interest.
Okay, that is somehow, that should be quite big, but yeah, it's also somehow dependent on what kind of gates you're using, because somehow if you're able to do the direct Toffoli, that already saves you like 10 gates, more or less. So, okay, I don't know what is the smallest useful algorithm that you can do in this model. Let's say, yeah.
Thanks.
Okay, so while the next speaker sets up, let me ask you a final question. In adiabatic quantum computing, one of the great attractions is that the system stays in the ground state the whole time, so you do not have to worry about T1.
Yeah.
And here you're purposely introducing an excited state.
Yes.
So is there a way to avoid that and go back to fully adiabatic?
Okay,
or
so
ground state? Yeah.
if there is a way to avoid that, I have some ideas to avoid that, but then that would complicate. So let's say with Transmen qubits, that would be somehow difficult in a certain sense. Because, I mean, you should somehow rely on, let's say, an intrinsic protection of the qubit itself. But like a way of curing this, I mean, you can try to cure this, but then you would lose the fact that the scheme is completely passive somehow. So that would be a requirement for sure. Yeah.
Okay.
Yeah.
Thank you.